We are going to present horse use case 1. In this use case, we will show how a malicious UE from UPC attacks an Afasek metro station panel located at Iumu. We will present both scenarios, without using the horse platform, and with the horse platform enabled. Initially, the UPC train simulators generate normal traffic towards the Iumu panel. At a certain point, one UE becomes malicious and attempts to deny the service through a flooding attack. We will now observe the Iumu panel. Initially, it is operating correctly, receiving real-time updates from the simulators. These simulators are running from 3 UPC UEs, which continuously update the train positions while probabilistically introducing delays or early arrivals in order to emulate realistic operational behavior. As can be observed, the train positions and timing data are continuously updated in the corresponding panel without any kind of incident. Here, we can observe on the Iumu gateway router how the requests from the UPC simulators are received. Suddenly, one of the UPC UEs becomes malicious and starts launching a flooding attack. Shortly afterwards, the panel becomes unavailable due to the saturation caused by the attack. In the bottom right corner, the amount of incoming traffic can now be observed. If we take a closer look at the router traffic, we can observe a flood of requests coming from the attacker with IP address 10.45.0.5. As no mitigation has been applied to the attack, the service remains down until it is resolved by the technical support team. We'll now show the same flow, but in this case, using the horse platform. The scenario is the same as before. The simulators are located at UPC, the dashboard is hosted at Iumu, and suddenly, one of the UPC UEs starts attacking. The difference is that, thanks to the horse platform, the attack will eventually be mitigated, allowing the system to return to normal operation. As in the previous case, the video shows that the panel initially operates normally and is updated by the UPC simulators. Suddenly, one of the UPC UEs becomes malicious and starts attacking the panel again, generating a flooding attack. After a few moments, the panel goes down once more and becomes unavailable due to the saturation caused by the attack. In the bottom right corner, the traffic volume captured at the Iumu gateway router can be observed. From this point onwards, the workflow of the horse platform used to mitigate the attack will be shown in the top right corner. As a first component, smart monitoring processes and normalizes raw data, exchanges information with the preprocessing module, and forwards the resulting data to the early modeling component and the profiling and prediction network digital twin. The early modeling component receives information about potential cyber attacks together with the network context. Based on this information, it generates an attack model describing the scenario. This model is then sent to both digital twins. The prevention and prediction digital twin receives the policy and starts executing its prediction process. In parallel, the impact analysis digital twin also receives it and remains on standby, awaiting further instructions from the IBI. As can be observed, at this stage there is initially no simulated attack in progress, nor any mitigation applied on any router type pod. Once the PPNDT completes the prediction process, it generates a JSON object containing the detected attack type, DDoS downlink, together with its associated confidence score, 0.6, and sends it to the DTE. The DTE receives the prediction, creates the corresponding intent, and then sends it to the IBI. The DTE intent request reaches the IBI with the threat identified as DDoS downlink. At that point, the IBI queries the CKB using the attack information contained in the received intent, and the CKB returns the associated mitigation strategy, block pod address. Once this is validated, the loop with the impact analysis digital twin begins, where the attack is simulated and the mitigation is applied in order to evaluate the impact both with and without mitigation. We can now observe the IANDT. On the left-hand side, the policy translator is shown, displaying a monitor type action requesting that the attack be replicated, On the right-hand side, there is an internet pod representing the external attack source, where we can observe that the attack is being actively simulated. After a few seconds, the packets per second metric is collected from the victim pod, DNS-C1, resulting in a value slightly above 10,000 packets per second, and this information is reported back to the IBI. The IBI receives the response, updates its internal state, and then proceeds to issue the mitigation. The IA-NDT receives the mitigation instruction. Block the IP address corresponding to the attacker pod on the CEOS2 router so that its traffic can no longer traverse the network. After a short interval, the policy translator instructs the orchestrator to apply the countermeasure, and we can then observe it being enforced on CEOS2. The metrics are then analyzed again, and we observe that the packets per second value measured at the victim is now 0, which is then reported to the IBI. At this stage, the IBI is waiting to receive the mitigation outcome. If the result exceeds a predefined threshold, in this case, a substantial 90% improvement in the measured metric, the mitigation is considered successful. The IBI then provides this result to the CAS, which must validate the action before it is sent to the RTR. In the CAS dashboard, we can observe that the action has been approved. Once the action has been approved, the workflow is sent to the RTR, indicating that for that specific threat, the corresponding countermeasure must be enforced on router 2 in the infrastructure for the external IP associated with UPC. The EPIM is responsible for translating the actions received from the RTR playbook into infrastructure-specific configurations and delivering them to the dock. Once it reaches the dock, it's responsible for instructing the corresponding infrastructure orchestrator with the specific configuration, following its policy format, in this case, MSPL. At this point, the action is applied, and the IBI is informed that it has been successfully enforced. The IBI then indicates that the threat has been mitigated and the intent fulfilled, bringing the workflow to an end. Now we can take a closer look at the infrastructure. On the left-hand side, we can see that the dock policy has reached the orchestrator and how it is being applied. In the bottom right corner, router 4 is shown, where it can be observed that the attack traffic is still arriving. However, if we look at the top, at router 2, we can see that the policy has already been enforced. If we capture the traffic on router 2, we can observe that the traffic associated with the attacker is no longer forwarded, and that only the requests from the panel simulators are still reaching the destination. Once the mitigation is applied, we can observe that the attack no longer disrupts the dashboard, which returns to normal operation as the network is no longer saturated. From the attacker's perspective, we can now observe that the packets are no longer reaching their destination, as they are being blocked at the router located upstream from the panel. If we examine the panel logs, we can see that the panel remained unavailable for 117 seconds, during which the full prevention workflow was completed using the horse platform. In a scenario without the platform, the technical team would first need to detect the attack, manually apply a countermeasure, and travel to the incident location, which would take approximately 2 hours. This represents an improvement of approximately 95 to 99% in response time when using the horse platform. This concludes with the demo associated with the use case. Thank you very much for your attention.